Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Jia-Wei Wang with us today. Hey, Jia-Wei.
Hello, Frank.
How are you?
I'm good. How are you?
Let's see. On this March 1, so we're coming up on Equinox 2021. I'm doing quite well in Phoenix, Arizona. And so where are you located?
Now I'm in Taipei, in Taiwan.
Taipei. All right. So we got some kilometers between us. Halfway around the world. So is it starting to look like spring a little bit in Taipei?
Well, the weather here is not very stable at this time. So it sometimes rain, it sometimes so chilly, but it sometimes become hot. So yeah, it's hard to say.
Okay, in a transition zone before we enter equinox here soon enough. So very cool. You look like you're in your office. So are people out in their office where you're at?
Not this time. So we have a quite flexible working schedule. So people prefer to come late.
Ah, okay. Okay. But you're not at home. You're in an office, I think. So
yeah.
Very cool. All right. So Jia-Wei, what do you like to do for research?
So what I'm interested in is about the complete story of the star formation. So as you know, the star formation is a quite long process. It might start from the molecular cloud at a larger scale, and it will go down to the filamentary structure, then go down to the cluster or some dense cores, and go down to the stars and even disk and planet. Right. So what I'm interested in is to study the whole story of this multi-scale process. Cool. So I need to use a lot of different instruments. For example, we need maybe optical or single dish telescope to map the large scale cloud, and we need interferometer to go down and study use the high resolution observation to probe the young stars or even the disk or even a planet. So actually I have trying to use a lot of different instruments. For example, I try to use the optical infrared telescope. I use the single dish radio telescope, and I even try to use the radio interferometer. So what I want to do is to combine all these kind of different observations and give a full story of star formation.
Cool. Very nice. Very nice. And in fact, that is going to bring us to this very lovely APJ article on formation of the Hub-Filament system G33.92 plus 0.11, local interplay between gravity, velocity, and magnetic field. And Jia-Wei, take us away.
Okay. So about this article, this is just like as I say, I want to know the full story of star formation. So this is just a one step. So this Hub-Filament system is just a commonly seen morphology of cloud that is associated with massive star forming regions. And actually, this target has already been observed by ELMA. So we already have high resolution data to see there is a massive protocluster forming in the center of the system. Okay. And in this article, we will use the single dish telescope to observe the environment of how this protocluster form from the large scale cloud. And in this article, we want to highlight the analysis focusing on the local aspect. So yeah, I will talk it later.
Okay, cool. Very nice.
Okay. So we can move on to the figure 1.
Let's go to figure 1. Here we got some stuff about the JCMT pole-2 observations.
Yeah.
And it looks like we got some polarization stuff going on there, PUQs. So that's how you're going to be telling certain things. And in fact, here we go. So figure one.
Okay, so we can just see the map first. So this map just show a Hub-Filament system at parsec scale. So you might not see the hub clearly. You might not see the filament clearly, but you can already see a very bright, compact object in the center of this map. So
Yes.
that is the hub. And you can see there are some extended structure to the south, to the east, and that is the filament. And the massive product I have just mentioned is in the very center of this region. So you cannot really see this by this map because this map are probably in the larger scale structure of the environment of this protocluster. So what we observe here is the polarization of the dust continuum. And typically in this industrial median environment, we could assume that the dust grains are aligned with the magnetic fields. So we can use the orientation of the polarization to trace the projected magnetic field morphology. So here in this map, those segments are just showing the magnetic field orientation projected on the plane of the sky. So we are trying to use this kind of method to know the overall magnetic field morphology. And later we will discuss how it correlates with other physical parameters.
Question: what's the difference between what's the difference between the yellow segments and the white segments?
Oh, it just show the data selected by 2 sigma and 3 sigma. So yellow is 3 sigma and white is 2 sigma.
I'm with you. I'm with you. Okay, cool. Nice image. Slide down.
Okay.
Okay.
So let's move on to figure 2.
Stop.
So in addition to precision data, because we want to know how different physical parameters affect each other. So here we use the around centimeter CATO data, and here we mainly want to use the velocity information extracted for this data. So here I show 3 panels. The left one is the total intensity. Here we just want to show we can see roughly the same structure like what we see in the dust continuum. So we can confirm that the CATO here are tracing roughly the same structure as what we are seeing in the dust continuum. They are associated. And the second part is the centroid velocity. So we want to know what's the velocity of the gas and how it interacts with filament and the magnetic field.
Okay.
And the third one shows the velocity dispersion. This will be used to account for the strength of the local turbulence.
Yes. Okay. Nice. Very good.
Okay, so then we can move on to the figure 3.
Ooh, more complicated here. Okay. Pull that down a little bit. Okay.
Yeah. So here shows how we find out the filamentary structures. Here we use the algorithm called disperse. This is also commonly used by the Herschel telescope global team. They use this algorithm to identify the filament within a cloud. So here I try to use two different thresholds to identify the filaments, and you can see there are two lines with different colors, green and cyan, and actually the morphology are roughly similar, but so that you can all see there are filament that is first connected. Most of the short filaments, they are connecting to the here I call it minor converging point. It's like the C4, C5, C6. So you see there are short filaments connecting to the local center. And after that, all of them will all converge into the major converging center, that is the C1 or C2. So you can see here the filaments are not random orientated and they are not parallel to each other. So they are just all going to the center of this system.
Right.
And also, as you can see here, so you can see a color bar here. I even need to use a log scale to show the intensity map. And that because the intensity here, it changes quite dramatically from the outside to the inner side. So it's actually different. It's very difficult for human to actually see the filament from the map because the change of the intensity along the filament is quite huge. So it's quite different to the filaments we find in diffuse interstellar medium.
Yeah, 20 to 5,000. Yep.
Yeah. So the right part is showing the same filament identified by just continue, but we overlaid it on the C18O intensity map. So here we're just showing that the filament can also, with the C18O data can really trace the similar structure, that can really trace the similar filament structures.
And we use the same disk per SE. Okay, good. Okay, I'm good. Yep.
Okay.
Very nice.
So we can move to figure 4.
Analysis. That looks pretty straightforward.
Okay, so this is just an example of a filament radial intensity profile. So if you go back to figure 3, some people may doubt that. Can you go back to figure 3?
Sure. And of course, we do have a little bit of a bandwidth lag between here and Taipei, so it's all good.
Okay. Okay, so well, I heard some people is doubting that whether this filament structure is true or not, because it's very difficult to directly see the filament structure. So here we just select a card as an example. So here we have a red line here to show a card along one of the filament.
Yeah, right
and the figure 4 is drawing the intensity profile across this red line.
Yes.
So in figure 5, in figure 4, this shows that we see there's a figure 4. Here we shows that there's indeed a peak along the red cut. So just here to show you that this filament is real. It's not due to some mathematic magic.
Right. There's something real there. Very good. Okay. Yeah.
Okay.
You got a beam. It's detecting something. And figure 5. Deconvoluted filament widths. Okay.
Yeah.
Decrease that.
So in the previous papers, like the statistics from the Herschel-Gilbert survey, they find that the filament, the interstellar filament, they are likely to have universal width that is about 0.1 parsec. Okay. So here we're trying to calculate the width of the filament identified in this region to see if they also have the same property. But here you can clearly see the filament width here is actually about 0.5 parsec. So it's quite wider than the interstellar median seen by the Herschel. Right. And here the panel B, we also show how the filament width change with the filament ridge intensity. So the filament intensity in here, we have a higher intensity in the near the center of Hub. So here the intensity is also roughly increased with the distance to the Hub. So we could find here that the filament width is also slightly increased from the the diffuse part to the dense part. So this is quite different from what people find in the filaments in the interstellar medium. So we can know that we are probably not seeing the same type of filaments in the stellar medium. So here we can know that there might be a different type of filaments. So in the previous statistics, people are trying to summarize the common properties of all the filaments in a lot of different molecular clouds. But here we are focusing at this region, and we can know not all the filaments have the same property as others. So it's important to have to study the filaments like in different environments, so we can see how they. So we can see what's the difference between them. Okay.
Okay, you want to talk a little bit about the green bar here?
Oh, yeah. So the green bar is I will discuss this later, but this is mainly to show what's the critical mass, of this filament. So okay. So when the mass of the filament increase, if it reaches the critical mass, then it might be gravitational unstable and it could start to fragment. And here the red line is just the estimate of the critical mass. So below this mass, the filament is more likely to be gravitational stable and they can be well stand.
Okay. Okay, good, thank you.
So now we already identify the filaments from this region. So what we want to do further is to see how gravity interact with filament and with magnetic field. So in the figure 6, we're trying to estimate the gravitational vector field based on the dust continuum. So here we made the assumption that the current density of this cloud is traced by the dust continuum, and we use the dust and we use the current density as a proxy to represent the mass distribution. So we could estimate the direction of the gravitational force. But actually here this estimation relies on some assumptions, like most of the mass are roughly in the same plane, are roughly at the same plane. So like the left half and the right part, they are not very distant along the side of side. So yeah, this is the assumption that we really need. So because, well, it's a fundamental question in astronomy that we don't really know the 3D structure, so we always need to rely on this kind of assumption to do the estimation. But we need to always be aware that this assumption might be always correct.
Right. Good.
Okay. So now we have the magnetic field, we have filament, and we have gravity. So the next step is we are trying to know what's the direction of the gas flow. So here we calculate the velocity gradient from the central velocity of CATNO data. So here the magenta arrows shows the local velocity gradient. So we use this to trace the direction of the gas flow.
The gradient, right? Okay. Not as organized as this one.
Yes, it's a little more complicated. We can see some tendency that this velocity gradient they are some in some places they seem to tend to be perpendicular to the filaments, but it's not always true. The direction of these arrows keeps change, and also the magnitude also change. So I will show that how it really correlates with the filament.
Okay. Awesome.
Okay, so next figure 8.
Okay.
So this is about analyzation. In this paper, we are trying to focus on the local aspect of the relative correlation between all the 4 parameters. Here we use the filament, we have magnetic field, we have gravity, we have velocity gradient.
Right.
And why we want to do this is, if you have seen the precession map from like 10 or even 20 years ago, you can see there are only a few segments. So at that time, people are only possible to do the analyze using what we call here the global aspect. That is means the average property of a whole system. And well, so if you see the max one, you can find that the intensity of this cloud is actually varies so much. It's from about 100 milliJoule to 1,000 milliJoule. So if you just simply do a global average over the whole system, is not really, well, we don't really know what the average means because it averages a very different environment. So in this article, we are trying to focus on the local correlation. That is really the correlation that is found in very similar environment. So here this figure just shows the first order comparison. We just see the distribution of the 4 parameters by itself. So here is the 4 histogram just shows the orientation of these 4 parameters by itself. And so from filament, you can see there are not some particular direction that are all aligned with. So because from the filament is converging to a center, so you can roughly see this might be all direction. But in magnetic field, you can see there is still some peak.
Yep. Yep.
Yeah, but from here, I just want to just show the overall histogram of the orientation, so we can move on to the next figure. So that will really show what's the difference between different parameters.
Do you make anything of sort of the a minimum here? I mean, this one almost looks bimodal.
Well, if you go to the figure 1.
Okay. Let's do that. Yes.
So in the figure 1 here, you can see the magnetic field are showing some pattern. So like in the northeastern part, they are like the position angle is about 120 degrees. So, but in the southwestern part, the direction is changing. But locally, they still have quite consistent orientation. So in the histogram, it just shows that this magnetic field morphology is locally quite smoothing. They have consistent orientation, but at different positions, the magnetic field morphology could change a lot.
I'm with you. I got it. Very good. Cool. Thank you. So that took us from 8, and now we've got some KS tests going on.
Yeah. So in the figure 8, we just show the histogram of the orientation of each parameter by itself. But here we are moving on to the comparison. So here you can see there are 6 histograms, and you see a label. It's the type of this 6 diagram. So this is to show the comparison between these 4 parameters. So we have 6 combination, that is, for example, magnetic field versus filament, gravity versus filament, velocity gradient versus filament, and here is just the relative orientation of these 6 parameters. And among these filaments, among these comparison, some of them does not really show a significant trend, but some we can see they are clear tendency. For example, in the gravity versus filament, we can see there's a strong tendency that they tend to be parallel, but in some others they are not so clear. So we need to use the KS test. This is to show how this distribution differ from the random distribution. So if here the p-value is small, then we can be more sure that they are not just random. So in here, if we use p equals 0.05 as the standard, then we can find that only the GBSF, VGBSB, and the VGBSG, these 3 sets have a smaller p-value. So these three combinations shows more strong, more significant trends, but others are not too different from random.
Yeah, like VG versus F. Okay.
Yeah.
Okay, G versus F. That would make some sense. Okay. And then the cumulative distributions.
Yeah. So this is actually the same as previous plots, but here I just plot it in cumulative histogram, so it's easier to show how it differs from the random distribution, that is the green dashed line. So you can find that like GVSF is clearly above the random distribution, and for like the VGVSG, they are slightly lower than the green dashed line.
Yeah, a little bit.
Yeah. So the next figure.
Yeah, we got a triple stack of orientation maps.
Yeah. So in the previous histogram, we just put all the segments into comparison. So we actually don't have the spatial information in those plots. So here we are coming back to the maps. So we can really see how those relative orientations are in the map. So here, these three plots are the example of the magnetic field versus filament, gravity versus filament, and the velocity gradient versus filament.
Yep.
And in each map, I show I show 2 plots of the physical parameter, and I also label the colored circles that shows the relative orientation between these 2 parameters.
Got it.
So
that's cool.
So you can really see here the blue points means these 2 parameters are roughly parallel, and the red circles means they are more likely to be perpendicular. So in here you can see the relative orientation has some spatial tendency. So for example, for the BVSF, it's more blue when it is close to converging centers like the C1 or C5.
Yes.
But actually, there are still some parts shows red when some of the short filaments, they are red, and they are connected to the local convergence point like C3 and C2 and C4. So so here we can find that this relative orientation is somehow correlate with where it is. And for the middle panel, we could see for GVSF, in most of the places, they are show quite blue. So this means the filament is quite aligned with the gravitational force.
Cool. Yep.
So in the bottom panel is the comparison between the velocity gradient versus filament, and it's more messy than the previous two,
Yes.
but we can still see some trend that they are more red when it is not close to the center, but in the center it becomes quite complicated. Sometimes red, sometimes blue, sometimes gray. Yeah. So here I can show some tendency that this correlation are changed with the position, and it's because this source have a very high density in the center. So the spatial dependence also means the dependence on the local density. Yes. So let's move on to the figure 12.
We get another triple stack. Yep.
So this is also the relative orientation between two physical parameters. And this is the same 6 combination. But the only difference here, we separate our data to different density. So it could be diffuse area, that is the outer part of the system, and it could be in the dense area that is more close to the center hub. So here we want to see how this correlation changes along with the local density. And in some places, we can really see difference. For example, the magnetic field versus filament. And
okay.
Yeah. So the magnetic field versus filament, in the diffuse part, they are quite random. But when we go into the dense part, we can see there is a strong tendency to be aligned.
Yep.
And in some other case, like the gravity versus filament, they are always parallel. They are always parallel to each other, no matter you are in low density or high density areas. So here I want to show that these correlations are actually really depends on the density. So it shows some kind of evolution from how the role of this physical parameter changes from how this role of these parameters evolves from low density to the high density region. So can move on to the next.
Very good. Very good.
The table 1. So, well, in the previous session, we are performing some statistics to see how these parameters interact with each other locally. But here we still using some old way. We calculate the global average value of this system. So we calculate the magnetic field strength using the Chundro-Sikafumi method. We estimate the energy between the gravitational energy, that is the W here, and T is the kinematic energy, M is the magnetic field energy. So here we estimate the relative scale of the energy. So we do this calculation using circles with different radius. This is shown in the figure 1.
Yes.
So we use different radius to trying to still get some spatial information that how is the energy scale of these 3 parameters change in the in the biggest area to the smallest area. But here we can see that the ratio are not changed too much. They are roughly all much less than 1. And this means that the gravitational energy is much greater than the kinematic energy and the magnetic energy. So this tells us that in this system, gravity dominates the kinematic energy and the magnetic energy. So even you combine the magnetic field and the turbulence, you cannot support the cloud from gravitational collapse. So from this analysis, we can conclude that this system is dominated by gravity and is likely collapsing. So this actually is consistent with our analysis that the filaments are quite aligned with the gravity. So then here we can speculate that the filament is probably dragging by the gravity, and because these materials are collapsing, so this filament is likely the accretion materials that is converging to the center.
Yeah.
Okay, so
neat.
We can. Yeah, so I think I will skip this figure because this is just the way we calculate the magnetic field strength, and it's a little technical, so we can skip this figure. Okay, so in addition to orientation, we are also interested in the magnitude of the velocity gradient. In here, we can see that here we can see that the magnitude of velocity gradient have some special tendency. It is often larger in the outer part of this cloud, but becomes smaller in the center part of this cloud. And here we are comparing to the velocity dispersion. There is another velocity information extracted from the C18O data. So that is the figure 15. So in the figure 14, we shows the magnitude of velocity gradient, and we also have magnitude of velocity dispersion. So here is showing how these two quantities correlate each other. And we can find that here is an anti-correlation, that if you have a velocity gradient, you have a higher velocity gradient, then the velocity dispersion becomes lower. And it's actually a little special because, well, if we assume if we have a system that has higher velocity gradient in all direction, then we will expect we will have also measure higher velocity dispersion in this area. But what we see is different. If we have higher velocity gradient magnitude, then we got lower velocity dispersion.
Yes.
So we are trying to find out what's the possible reason. And here we add the information of local density, that is the color of this point. And here the red color means high density, blue color means low density. So we find that this line are also correlate with density. So we speculate this might be caused by the local density, and this is also the effect of evolution. So here the velocity dispersion are usually be in the velocity dispersion in star formulation are usually be taken as a effect of the local motion, and in massive star formation, we know because the mass will be collapsed to form stars, and this motion will generate a lot of complicated dynamics in some in the high density region. So normally we can measure the velocity distribution is higher in the high density regions. So this makes sense. But here we see the velocity gradient magnitude show different trends. So this is actually related to actually this is so to know why they are different, we need to know what we are measuring here. So the velocity dispersion here is when we measure a C18O at one position, we have the velocity information along the line of sight. So we actually include all the velocity component along line of sight. But for velocity gradient is quite different. So to calculate the velocity gradient, we need a map with given resolution. So we need to calculate velocity. So the velocity gradient is calculated with a map with given pixel size. So for example, in our case, the pixel size is 4 arcsec. So if we calculate velocity gradient at this given pixel size, this is actually only reflect the velocity information at this scale.
Yes.
So these two quantities are in fact tracing the motion at a different scale. So velocity dispersion traces all velocity components, so it reflects all the motion at all scale, but the velocity gradient also represent the motion at given scale. So from this plot, we can see it actually represents that the scale of the gas motion evolves with the density.
I'm with you.
Okay.
Very
so
good.
Yeah, I think we can move on to the figure 16. So this is just a scenario we are proposing, trying to explain what we are observing. Right. So we have filament, we have magnetic field, we have gravity, we have velocity gradient to trace the gas motion. Right. So for the gravity part, it's more simple. So we think because this cloud is dominated by gravity and everything should be collapsed. So here for gravity, the simple explanation is that everything is dragging by gravity. So we see filament as accretion flows, they are flowing toward the center by the gravitational force. So we see everything is perfectly parallel to each other. And for gas motion part, because here our resolution is not really, we don't have sufficient resolution to really see the detailed gas motion from outside to inside the filament. So what we can see is just the white arrow showing here. This is just an average along a bigger area, and we see they are perpendicular to filament in the outer part, but become more complicated and random in the middle part. Yeah. So we speculate that this is probably means that in the outer part we see the minor filament converging to the local center. So this probably means that the gas is flowing to the local center and converging to the longer filament. So in this part, the motion of the gas is perpendicular to the filament. But when it approaches to the center, the gas motion will eventually be dominated by the motion moving toward the center. So in this case, we have motion that is perpendicular to the filament, and we have a motion that is dragging everything to the center. And the mix of these two kinds of motion is not always could be very complicated. It depends on the resolution of and also the size of the filament. So we cannot really see not see the pattern when when the gas motion approach the center area. And for magnetic field part, it's quite similar because we don't have sufficient resolution to see the detailed magnetic field morphology. So what we see is just the orange segment that is, well, a little more random in outer part, but becomes more aligned to the filament in the center part. And that can also be explained by the scenario here that in the outer part, the magnetic field and the turbulence, they are comparably important, and they are at that part, the gravity are not so strong, so the magnetic field can be more random. But when it approaches the center area, density increase, the gravity increase, so everything is dragging by the gravity. So the magnetic field is aligned with the filament. So we are trying to use this scenario to explain what we observe, to explain the local correlation we find. So yeah, this is the main conclusion of this paper.
Very nice. I like this. I like this illustration.
Yeah.
Very nice. Very cool. Yeah. Lost my cursor there. Very nice. Cool. So you hinted a couple of times on where some future directions might lie. So where do you think the community goes over the next 5 years? Are there new observations, particularly maybe at higher resolution, to pick up some of those filaments? Are there different wavelengths one could look at? Just sort of where do we go over the next 5 years to help resolve this?
Well, there are a lot of things we can do. So for example, in our cartoon figures, we show that we don't really have sufficient resolution to see the correlation from outside the filament to the inside the filament, or even going to the center. So one thing we could do is to combine the single dish data with the interferometer data, so we can really resolve the structure from outside to inside the filament.
Nice.
And also here we only show the analysis onto one object, but this is not enough to really, we don't know if this is common case or they are special. So now we have a lot of precision survey, like in ZSNT. Using ZSNT, I also participate the Bistro survey. It's a precision survey toward many different star formation regions.
Yeah.
So I would expect we can have a lot more samples from this survey, so we can apply our analysis method to all this data, so we can have a fair statistics. And in addition to observations, we are also interested in how to compare the simulation result to the observational data. And our analysis is just one possible way to do a comparison, because as you can see, we can have a six histogram to describe the correlation of all these physical parameters detailedly. So we can have more detailed parameters that can be compared to the simulation data. So actually, we are quite interested in cooperating with theoretical people. So we want to know what's the expectation to this local correlation.
Very cool. Nice. The future is bright. I think there's going to be a fair amount of work in this field over the next 5 years or so.
Yes.
Very nice. Jia-Wei, I want to thank you so much for spending some time and walking us through your article.
Okay, thank you.
All right. Thank you, everyone. And we will see you on the next one. Bye-bye.
Bye-bye.